So as John mentioned, we definitely get the feeling that you guys are working on these individual parts, but you may not have the best sense of how it all fits together. So this is a general overview of how electrical vehicles in general work and how your part plays with the bigger picture. So this is a general overview of what a modern automobile looks like, right? So this is a gas engine vehicle. This is a forward wheel drive. So you have your fuel tank in the back, you have a tailpipe, muffler, all that. I'll put these slides up, I'll email them out so you can investigate it more closely. But this is kind of where we want to start, right? We are not reinventing the wheel or reinventing the car. We're going to base a lot of our designs and a lot of what we're doing off of what has already been done. So if you look at this, a lot of it actually doesn't change much, right? We'll still have a suspension system with these struts here, and we'll still have an engine, and we'll have a differential maybe if we ever get to that. So not a lot of things change, but what changes is how we execute and how we achieve movement. But the first thing we want to talk about is the frame. So chassis, this semester you guys started off with a space frame. And one of my favorite cars is the Ariel Atom, and it uses a space frame. So you can see that it looks very sleek, and a lot of the tubes are exposed, and it has some body members in the front. What is so nice about this is actually that it's one of the most weight efficient designs possible, because you can really manufacture this three-dimensional element to your liking. You can make it look great, you can make it really strong and stiff, and also save the most weight. The problem is, as we will probably find when we move into Formula, it's really difficult to manufacture this well, repeatedly, and to high accuracy. All these tubes have to be bent to a very specific radius, and they have to be cut to the right length and mitered. So that takes a lot of time, a lot of money, and welding it can also be a great expense. So how all modern cars today on the road are basically built using a monocoque or a uniframe design. Probably all the cars you drive will have this kind of layout. So on the top left, or on the top left, you'll see kind of like a SUV kind of a monocoque, and you'll notice that certain sections of it are highlighted. So these highlighted sections are members that experience the most stress. And we'll note that the windshield pillars are the A pillars. You'll have the B pillars, which are the ones in the center, between the two doors, and you'll have C pillars in the back. So basically a monocoque combines folded sheet metal to form a rigid frame. So these stressed members are designed in such a way to maintain the same structural stiffness, but what's so great about this is that it's all sheet metal, so we can easily stamp it out and manufacture thousands, perhaps millions of these over the course of many years. On the bottom right, you'll see the tub from a Lamborghini. So what Lamborghini does is a hybrid monocoque design. So the front and back are aluminum space frames, and then they're bolted into the tub. And it's an amazing process to watch it put together. If you really like watching cars put together, How It's Made has a great series on supercars and the manufacture of supercars. The difficulty of monocoque is actually, if we made it out of steel or aluminum, the high cost and weight of this vehicle. So as you might imagine, your vehicles weigh somewhere on the order of a ton and a half if it's just a regular sedan, and that's because the sheet metal is very difficult to make lightweight. In order to press it, and in order to form it, and in order to make it strong enough, you need to add many layers of sheet steel, and that's going to add up to weight. But because we value time and ease of manufacture over weight in passenger vehicles, that's why we make them this way. With Lamborghini and a lot of the performance vehicles, like the tubs will be made of carbon fiber, and all Formula One vehicles use some kind of composite material in the construction of their frames, because not only can they get a really nice, sleek-looking aerodynamic body, but it can also save weight. Because carbon fiber has that great strength property, this is why a lot of the cutting-edge technology uses composite materials in a monocoque frame. So that's chassis in a nutshell, right? We have this system of tubes or sheet metal that provides a really rigid and structurally sound mounting point for our traction system, right? If you think about the early cars, like everybody's probably seen a Model T, but even if you look at some of Porsche's early work when he was building carriages, it was all essentially a platform for wheels, right? And the only reason why we have these shells is to provide us better turning, better handling, and protection in the event of a crash. But if I could have it, I would sit on a board with 4 wheels, right? Because that's the lightest and most efficient use of material. But traction is the biggest thing for us. So for those who are new to this kind of concept, we're going to talk about gasoline automobiles and how they move forward. So here we have a rear-wheel drive car. A lot of cars today are front-wheel drive, meaning your 2 front wheels are the ones that are applying the torque and getting traction. But it's actually easiest to see how a vehicle moves with a rear-wheel drive car. So you have your engine in the front of the vehicle, so the front of the vehicle is on that side, on your left, the far left. You have the engine, which then ties into a transmission. The reason why we have a transmission is that gasoline engines operate in a very specific band. There's a specific RPM and torque band where they're most efficient. So you want to keep your engine in this band at all times, or as much as you can. But you may be moving faster, you may need more torque. So the way we do that is we change the gear ratio, right? If we need more torque, we go to a lower gear ratio. We might gear it down even. If we need to go faster, we gear it up so it's spinning faster, but we don't have that torque. That is then transmitted via the drive shaft to the rear 2 wheels. And one of the big issues that powertrain is dealing with is how do you get these 2 wheels to spin at different rates, right? Not just in the case of a turn, but if you hit an oil slick, if you hit a patch of ice, you're going to need one wheel to spin at a different rate than the other one because of differences in friction, differences in torque, right? So we have an element called a rear differential. And essentially what this is just a little tiny gearbox that allows the 2 wheels to be coupled when you want it to be coupled and decoupled when you don't want it to be decoupled. There are many different types of differentials, and I could give you a 15-minute talk on differentials alone. But kind of the brief overview is we started with an open differential where the 2 wheels, when they wanted to spin at different speeds, would just spin at different speeds. Now we have a limited slip differential where it needs to meet a torque threshold before they disengage and decouple. We also have aux lockers, electrically actuated things. I can go on for days. But one of the major elements I want to talk to you about is on the right, which is called the torque converter. And this is what makes automatic cars possible. So like I said, there's a very specific power band that the engine needs to operate in. So you want to be operating at the most efficient torque for the given driving application. And that's why you're shifting in and out of gears. But people are lazy, I don't want to be shifting all the time, so I have a torque converter. Basically, this is a mechanical device that says, okay, the wheels are requiring this much torque, this is what gear you need to be in. But unfortunately, it always is running, so it'll consume more gas than a manual vehicle. So now we talk about electric automobiles. And this picture here is actually the bottom half of, I think, the Model S 85D. It has 2 motors, front and back, and then it has McPherson struts on each of the wheels, and that bottom base plate is actually all batteries. But the theory of operation behind an electric automobile is super simple. You have, on the top image, you see a foot pressing down on a pedal, which is essentially a giant potentiometer, and that goes into a DC controller. You have batteries on the left and the DC motor on the right. If you increase the throttle, it's going to allow the DC converter to have a higher duty cycle. So you see those little square looking waves on the bottom? You can imagine that this averages out, right? So if those square waves were on 50% of the time and you had a battery pack that was 100 volts, then 50% of the time would translate to 50 volts, that the DC motor would see 50 volts over a long period of time. If I was on all the time, then 100 volts is going to the DC motor, 10% of the time, 10 volts. And so the theory of operation behind electric automobiles is actually very straightforward. The tricky part is actually what happens inside that DC controller box, and I'm sure Powertrain can tell you it's not very easy to build a robust system for electric automobiles. But ultimately, the system diagram and the way we look at things is actually a lot less complex than gasoline vehicles. So not only is the power transmission from batteries to the motor more efficient, electric motors can be 90% plus efficient. It's also just simpler overall, and simpler and less complex means it's going to be more efficient. And I just threw this picture up here to kind of give you a sense of how the whole picture looks together. So this is the Mercedes SLS E, and one of the biggest problems that we have with modern electric vehicles is just the sheer weight of batteries. So I think in a few weeks we're going to talk to you about different battery chemistries, but as you can see here, the bulk of the car is filled with high voltage batteries. And that's because, you know, this is a high performance racing vehicle. It needs a lot of power, and as a result, it needs a lot of batteries. One of the biggest things you're going to hear when talking about electric vehicles is the concept of energy density. So energy density is the amount of energy stored in per unit kilogram of material. So gasoline and fossil fuels are actually some of the most energy dense materials we know. In thermodynamics, you're going to cover this a little more, but for example, propane. 1 kilogram of propane contains 44 kilojoules. You know, gasoline contains 13 kilojoules, and for comparison, the best lithium-ion batteries contain 8.8 kilojoules per kilogram. So we're dealing with an order of magnitude less energy density, and we're trying to make that up with efficiency, but currently, we're not there yet. So how do you actually move these wheels? Well, there are actually 3 major types of motors that we want to talk about when discussing electric vehicles, right? So the first is brushed DC, and it's the one that we've all been using. You've probably seen this in, you know, any kind of electric toy that you've used in your life. What's really nice about this is that it's really robust. It's almost bomb-proof. The basic theory of operation of how a DC or a brushed motor, or a motor in general, electric motor works, is best described in this next slide. So I'm going to go back to brushed DC a little bit, but essentially the way an electric motor works is it uses a traveling magnetic wave. So in this picture, you're seeing 2 parts. The outer ring in this kind of circular configuration here, this outer ring is what we call the stator. The stator is the non-moving part, it's stationary. The inner ring is the rotor, it rotates. And on the rotor, you'll notice that there are north and south permanent magnets. So this is what is called a brushless DC, PMAC, or a permanent magnet brushless DC motor. So what is happening here is on the stator, you see a bunch of coils, and those coils are acting as electromagnets. We can turn those magnets on and off based on the input wave signal on the left. So if we wanted to rotate right, we commutate the rotors, the electromagnets in a, you know, clockwise fashion. Or if we want to reverse it, we turn it into a counterclockwise fashion. For these brushless motors, the way we dictate speed is actually not through PWM, but through frequency. The faster at which we are rotating, switching the magnetic field, the faster the rotor is going to spin until it hits a hysteresis point. But with brushed DC, we can see that it's a lot simpler. Notice there's this like little green cylinder in the center. That's called the commutator. And the reason why we need commutation is because what we're doing is we're changing current direction. Notice that now in a brushed DC system, the stationary parts are the permanent magnets on either side. And there is a rotor on the inside that is the electromagnet. What is happening is the electromagnet is going to be attracted to the south part of the magnet, of the stator, and then right when it hits the south part, the current direction inside the electromagnet is going to switch. Then it's going to be repelled from the south polarity magnet, and then it's going to be attracted to the north. And then it'll never hit an equilibrium point if it's properly designed. So what's so nice about brushed DC is that it has no need for any kind of special sensors to sense its position or commutation, and also it will always work. It's pretty foolproof in its function. Finally is AC induction. This is what Tesla uses in all their vehicles. It is potentially as complex as brushless DC, and Tesla uses it for its increased control. So what is actually happening here is the rotor in the center is no longer a magnet, but actually sometimes it is a squirrel cage, sometimes it's a ball of wire. And what is happening is you are actually inducing an electromagnetic field inside the rotor based on the electromagnets on the outside. So as you can imagine, just doing that is a really difficult task, and then having to vary that at speed and torque and actually change the strength of the magnetic field on the inside is very complex. But what Tesla uses it to do is to increase its efficiency, and it can actually operate on a much wider power band. And I know I'm throwing a lot of information out there, and I know that some of you guys are falling asleep, but it's all right. You know, the idea here is that it gives you a broad strokes overlook at how all these different components are fitting together. And this is supposed to spark a conversation between sub-teams, right? Now you kind of have the terminology and you actually know what to ask, right? You can go to powertrain, you can go to sensing to talk about something like the CAN bus. So this is the final piece of the puzzle. Modern cars today are more like robots than they are like a carriage. So there are sensors all over the vehicle. The top left photo can show you how, there's sensor boxes all over the vehicle. We might have, engine temperature, exhaust, the materials inside the exhaust, and how do we get that to communicate with each other? So the bottom right picture shows you the CAN bus. Notice how there's just one line and branches coming off the line. That is really awesome, because if we want to string a whole bunch of sensors onto a line, we run a central line down the center of the car and then run nodes off of it. We don't have to have each of the nodes connected to each other and make sure that everything is communicating together. Actually, in John's Mercedes, his car is from an era before the CAN bus. So if you were to undo his dash, it's just a rat's nest of wires, because everything that needs to communicate to each other needs to have a direct line, and it's just a nightmare in creating the wire harness. So this is a great way of simplifying the amount of wires that you need to run. And this is an example of just how much information the CAN bus can provide. So all your speed, your tachometer, your indicator lights, your windows, they're all controlled via CAN bus. So it is actually a critical component of the car. If you were to liken it to a human body, this is your nervous system, right? You are the brain, you're sending the control signals, but how it's getting to the various aspects of your car is all controlled via the CAN bus. So it's a super critical system in the construction of any vehicle. And finally is user interface, right? As engineers, especially as engineers in Olin, we can't forget that humans are using these vehicles and that we need to consider how they're interfacing with this vehicle. So this is a steering wheel out of a Sabre F1 car. And to me, I personally hate the way it looks. I think there are too many dials, too many buttons, and I think that it could be further simplified. Obviously, the reason why they do this is that there's so much control, right? All the different levels and all the different power settings are controlled through this one steering wheel. But again, this communicates via CAN bus, and this is the bridge, the link between driver and car. So yeah, that's everything. Questions, comments, concerns? I'm here to answer them for the next, let's give 3 to 5 minutes. Yes.
So if you had to simplify the difference between a brushed DC and a brushless DC motor in one sentence, what would you say?
Yeah. So it all comes down to commutation, right? So you see that green cylinder? That's actually physically connected to the electromagnet, right? And you see those brushes on the side? Those are usually some carbon graphite now, but they wear down over time, right? And those generate friction, those generate heat, and that's actually going to generate further losses. So you'll be hard pressed to find a brushed DC motor that's above 93% efficient. But you could definitely find brushless DC motors that are 95% efficient, because there's just not that physical connection between the rotor and stator. This is also why brushless DCs can spin up to much higher RPMs. It's easy to find like a RC brushless DC motor that can spin 10, 15,000 RPM. It would be very difficult to find a brushed DC that can match that. Yeah.
What sort of motor are we using?
We're using a brushed DC motor, partly because it's just so much easier to control. I mean, we're already having so many problems getting the motor controller to work. Could you imagine if we had to now have this complex sensing algorithm? So you see these square waves that you have on the left-hand side. The on-off states are actually dictated by the position of the rotor. Now there are 3 ways you can do this. You can use a Hall effect sensor, you can use an optical encoder, you can also use back EMF to calculate your position. A lot of cheap, low-cost brushless DC motors don't have Hall effect sensors built in, so you use the back EMF to calculate. It's incredibly not difficult, but frustrating to implement. So I would not recommend it. Yeah. Anything else from non-chassis members? Yes?
Why does Tesla use induction over brushless?
So I actually included this link to a blog post on induction versus DC brushless written by a Tesla engineer. I'll be emailing this out so you guys can see that link. It provides a good and interesting look, more than I can explain to you in a few minutes. Yeah. Sensing, don't tell me that you have no questions about suspension, torque conversion, differentials, chassis design, construction.
I don't know what I don't know, so.
Oh, I see. So do you know why it's important for a frame to be stiff, but not too stiff?
You want it to crumble, but you also want it to be structurally sound.
Yes, in the event of a crash, that is part of it, but actually in your daily life, you would experience the effects of stiffness as well. Yes, well, yeah.
No, I have a later question.
Okay. Okay, well, anyways, when you take a turn, you know, when you're taking turns in your big SUV and you like play that Jello game, you probably feel how like there's that acceleration, that centripetal force, right, pulling you to one side depending on your turn. Well, your car is also experiencing that. And if you imagine your car as a giant cylinder, it's experiencing some torsion, right? So if it's too stiff, then that torsion can actually fracture the car, right? Because it's brittle. You know, stiffness can actually be linked to brittleness. If it's too bendy, then you're going to lose a lot of that torsion, and then you could suffer fatigue failure. You want to hit an optimal torsional stiffness in your vehicle. In racing applications, we want it to be almost as stiff as possible because we want to have very little body roll in the event of a turn. Body roll leads to losses, inefficiencies, and a lower G turning. So in racing applications, when we take a turn, you know, the high-end cars can hit a 1.4 G turn. So that means that your centripetal acceleration is 1.4 Gs out of the side. That's really high, and it's hard to achieve. But part of that is making a very stiff vehicle that maintains a solid contact on the ground. Yeah, Lisa.
Okay, this is a powertrain question, obviously, because our powertrain would ask this. Why is suspension called suspension? There's absolutely no strings or suspending involved.
So actually, that's a great question, and I was going to dedicate a whole lecture to just suspension technology alone. But if you think about it, why have suspension, right? Why not have just a go-kart frame? It would be the best. It'd be super stiff. We can actually design it to be somewhat, yeah?
What? Not the question.
Oh, okay, well to answer your question most directly, it's because the center cavity of the vehicle is actually suspended, right? Because you see these big like tube things, those are struts. Those are, well, we use a different number of situations, but let's say they're coilovers. So they're springs, right? They're springs and they have dampers inside of them. So the central mass of the vehicle, the passenger, the cabin, where you sit in, the passenger, is actually supported purely by that spring, right? So you are suspended in a sense. We actually separate those two into two camps. We call it sprung mass and unsprung mass. So the sprung mass is where you sit and where the cabin is. The unsprung mass is where the wheel is, the knuckle, and all the associated components there. Yeah, there's a whole lot I can talk to you about in that space. You had a question?
Yeah, so you're talking about stiffness in the frame. Is that just the frame, or does that include the suspension?
So that's mostly, we look at that as the frame, right? So if we're going to do that analysis, I would take the mounting points for the suspension elements and lock them down, and then twist them and see what kind of torsional stiffness I get. For the suspension elements, there are several other factors to consider, right? Obviously, what we do in vehicles is, there's another good picture of this, we have anti-sway bars. So in your passenger vehicles, you actually want to have a decent amount of suspension travel, right? As you imagine, the roads, especially here in Massachusetts, are not perfect, lots of potholes. If you drove over a pothole with a really stiff car, you're going to feel it all the way up your back, right? So having a nice soft suspension, like what Baja has, will absorb a lot of impact. But the problem is, it's really bad for when you take a turn, because when you're trying to take a turn, the inertia of the vehicle wants to resist that turn, and that resistance is not transferred through the shock, right? The body wants to resist the turn wants to lean the body, so the shock is going to absorb it, and you're going to suffer in the turn, so your performance will suffer. So ultimately, it's a complex question. Right? How do you tune your suspension? How do you design your suspension? That's why suspension is considered the dark art of vehicle design. It's fascinating though. I would definitely recommend people to study up on it.